Okay. Perfect. Okay, my sound is on. Okay, great. Oops. Awesome. So I was assigned to do intermolecular forces, which is lecture 23. And up to this point, we've seen quite a few questions about intermolecular forces, but intermolecular forces are a part of our everyday lives, and I definitely did not notice until I took this class. But they're part of what makes the difference between how thick and viscous honey is, and then how liquid my conditioner is, right? And some other things that are affected by intermolecular forces are boiling point and viscosity, surface tension, capillary action, yes. And all these things, or I guess knowing about intermolecular forces can help us determine which compound will have that higher boiling point, or will be harder for us to separate or break the bonds, the forces within it. So as if you can, I'm sure you've seen it before, right? So when a bug is on water and it just kind of looks like it's walking on water, you know, kind of like Jesus, but not really, because Jesus, you know, Jesus Christ is just a miracle, right? But anyway, these bugs, they can walk on water due to the intermolecular forces, because that surface tension is affected by that. And like I mentioned, viscosity increases with the stronger intermolecular forces. So honey has a stronger intermolecular force than water. And likewise, capillary action. So the liquids rise up in narrow tubes, and the adhesion forces have to do with intermolecular forces as well, adhesion and cohesion. Yes, that is just kind of like a little aside. Perfect. So intermolecular forces, we have 6 of them. So there is London dispersion, dipole-induced dipole, dipole-dipole interactions, hydrogen bonding, ion-dipole, and ion-ion. And so these are just interactions between molecules. And as I mentioned, they kind of, we see the effects of these interactions in physical properties. All right, perfect. And so the first one I'm going to talk about is just London dispersion. And this is one that I've definitely have been told and have heard many times that it's one of the most common ones to be present. So like if we're given a question and it says select all that apply, typically it's a pretty safe bet to say that London dispersion forces are present. And why is that? Well, it's simply because they're so weak. And you will see here that I misspelled weak. Actually, I meant weak as in not strong, but you know, my brain is mush these days, so I misspelled that. And I may have other typos, but yes, London dispersion forces. And so it's basically, oh, I'm so sorry. Let me turn that off. I don't know what that's for. Okay, so it's basically when, like if you imagine a balloon, right, full of water. And so this balloon full of water is our molecule. And molecules have the electron cloud, right? And the cloud is basically just where these positive and negative charges can just float around freely and get mixed up and move around. So if you take this balloon, so imagine this balloon is full of water and it has little pieces of metal. inside it. I don't know how that would work. Hopefully it wouldn't pop, right? But so these little pieces of metals, let's say these are the negative charges. And I have a magnet in my other hand. And so as I bring the magnet closer to the balloon, that will draw all the pieces of metal to where I'm holding the magnet. If I move the magnet around, all the pieces of metal will follow it around, right? And so that's kind of what happens between two molecules experiencing London dispersion forces. One, the negative charges in one attract all the positive charges in the other. So it's almost as if there's two magnets in balloons and they're attracting to each other. And that will make all the magnets just focus on one side of the balloon where they can touch each other, and the rest of the water in the balloon is just free to just go wherever. And that's kind of like a visual of kind of what's going on with these London dispersion forces. And the tendency for the electron cloud to do this is called polarizability. I may be saying that incorrectly. I probably am. But that, as it says here, is a tendency for the electron cloud to distort. And like it says here, it's a momentary shift in electron density between two molecules. And I like how it says momentary. So I feel like that just kind of like reiterates how weak these are. And so they're very easy to break. Perfect. And so what are some things that affect these London dispersion forces? So some factors that can be taken into account is the size and the shape of the molecules. So the bigger the molecule, ideally the more area you would have for it to interact with another molecule, right? So if you think of like a little molecule the size of a marble, there's not a whole lot of area for it to interact with your hand, I guess. But if you think of like a big, not even a big, orange, considerably bigger than a marble, you're touching more area of that orange when you're holding it. It's kind of the same idea. So yeah, the larger the atoms, the more electron cloud that can be distorted. Yeah, larger atom, larger cloud, more positive and negative charges to move around and attract each other or repel each other. And I like how it also says the size. I talked about that, the shape. So if I have, let's say, take your hand and spread it out. When it's spread out, as if you're going to give somebody a high five, but let's say you really, really decide to stretch out your fingers and like put tension in them, that is a lot of space for your hand to interact with a hot stove, right? You're going to burn a lot of your hand, a lot of your skin, because more of your hand is spread out. So it'll interact more. But if you put your hand in a fist, then less of your skin would be exposed to the hot stove. And so that's how London dispersion forces that's how size affects the strength of London dispersion forces, because similar to the size, the open hand, more space for these clouds to interact and to attract each other and just to create this interaction. Because if you think of it as a stick that you're going to carry on your backpack, and you just tied it by one string, and it's a pretty big stick, right? This has your arm, and you tied it by one piece of rope. That stick's just going to be flying around, and yeah, the rope, it probably won't break right away, right? But if you tie it with more pieces of rope, let's say you go from 1 to 4 pieces of rope and tie it onto your backpack, it's more likely that it will stay there. And so likewise with London dispersion forces, the interaction is stronger because there's more points at which the positive and the negative are interacting within the molecule if there's more area for them to interact, if that makes any sense. Okay, and now we have the polar interactions. So we have all of these intermolecular forces, but within the intermolecular forces, we have these polar interactions. And the polar ones are, pretty much everything that's not a London dispersion force. So dipole, induced dipole, dipole, hydrogen bonding, ion dipole, and ion. And as we know, dipole. Dipole, induced dipole is just, well, see, I misspelled it again. Ignore that. It's supposed to say stronger interaction than London dispersion forces. And so what is it? It's when a polar and a nonpolar molecule interact. How does that work? The positive and negatives of two molecules interact. The negative, and positive repel. This creates the attraction between molecules. And so yeah, polar molecules have a more positive and a more negative end. And yeah, so the oppositely charged ends attract to each other. And for this type of interaction, for molecules of, I guess, like the same mass or size, the more polar the molecule, the higher the boiling point in this case. And so, like it says, it's stronger than London dispersion forces. So I guess like if we had a molecule that had London dispersion forces and dipole, and we were asked which one would be the dominating intermolecular force, it would be dipole. But we also have to take into consideration the size, right? So if one molecule is much larger than the other, dispersion forces will likely determine the physical properties. Perfect. And so now we have hydrogen bonding. And so hydrogen bonding is the strongest dipole-dipole interaction. And hydrogen bonding, the hydrogen is covalently bonded to nitrogen, oxygen, or fluorine. It's fluorine. Sorry, my brain is mashed potatoes right now. So, but I feel like that is a very good, I wouldn't say a good sign, but like a pretty sure sign of hydrogen bonding, especially if you draw out the Lewis structure. You can see if hydrogen is bonded to one of those three. And that will help a lot in identifying and categorizing the compound. And so why, I guess, does it have to be covalently bonded to those? Because the nitrogen, oxygen, and fluorine make the hydrogen very positive. Because if you guys look at a periodic table, or if you guys just memorize it because you're smart like that, you will know that nitrogen, oxygen, and fluorine are very negative. And so the very negative makes the positive even more positive, creating a stronger interaction. And as I said here, their small size also allows them to get closer to each other. And so hydrogen bonding in hydrogen bonding, the atoms will interact with, I guess, a nearly bare nucleus, which means that it doesn't contain a whole ton of protons. But yeah, these are pretty strong. And this is, part of what we see in water, H2O. And so I guess this is one that's definitely linked to surface tension, because we see that a lot in water. Okay. Now we have ion dipole. So ion dipole are found in solutions of ions. The strength is what makes it possible for ionic substances to dissolve in polar solvents, so like water. And yeah, it's a direct interaction between ions and polar molecules. Cations attracted to the negative end, and anions attracted to the positive end. And the strength depends on the charge and distance. So obviously, I feel like if we have, not I feel like, I know, if we have a more positive and a more negative molecule, that's just going to make it stronger. Like back to the magnet idea, right? If my magnet, if my blue magnet is very, very magnetic and my red magnet is very magnetic, then when I put them together, it's going to be very hard to pry them apart. But if my blue magnet's just kind of like, kind of magnetic, my red's really magnetic, it'll still be easier to pull them apart because in a sense, the charge overall is weaker. And the distance. And so if we're closer, it'll be stronger. If we're further away, right? Because you can hold two very strong magnets in your hands, and you can have them, let's say, a foot apart, and maybe have a little of a hard time pulling them apart if they're really strong. Typically, you'll be okay. And further out, well, it'll be harder for them to really interact or like attract each other as much. But when let's say you hold them like a quarter, like imagine a quarter, the width of that far from each other, it'll be easier. No, it'll be harder for you to hold them apart because they'll be so attracted and they'll just want to come together. Yeah, perfect. And so now we're going to go on and talk about ion. And so it's an interaction between ions, right? It's the strongest intermolecular force. And so that was something good to remember, especially when we come across those. I guess I'm just traumatized by those questions because I struggled with those. But if we have to order them and which one is a stronger intermolecular force, if you see an ion, that one goes first, strongest to weakest. And so this type of intermolecular force, of course, affects melting point, right? And so a solid at a room temperature will have a higher melting point with these type of interaction. And ionic compounds with multiply charged ions generally have a higher melting point than those that are like singly charged. And this is also what we see with salt, right? A cation and an anion attract. I'm pretty sure the salt, I guess you can't correct me because you're not here, right? But I'm pretty sure the salt creates a lattice with this type of intermolecular force. I'm trying to check my notes if I wrote that down. But yeah. Okay, and so when we come to those problems or any situation when we need to compare intermolecular forces and compounds, let's say we're given multiple compounds and we have to just name the intermolecular forces or decide which one will melt, which one has a higher melting point, which one will dissolve in water, which one will not dissolve in water, that type of situation. That is when this type of approach would be helpful. And so the first thing it says is to draw. So we draw the Lewis structure. I'm sure we're all comfortable with that. We've drawn so many. And so the Lewis structure will let you see, what's bonded to what. Unless you're just some type of super genius and you can just tell by looking at the equation, then you go. I don't know. You're amazing. But most of us can't do that. And so drawing the Lewis structure will help us see how it's bonded and what it's bonded to. And then find the molecular shape. Like I mentioned, the molecular shape can affect the strength of the intermolecular force based on the area that one molecule has to interact with another. And ideally, of course, if two molecules have a wider area due to their shape, I think of like a pancake versus an egg, right? If they're both pancakes, then they have a lot of space to interact, which will make it stronger overall. But if we have a pancake and an egg, it'll be, the pancake has a lot of area, but the egg does not have a lot of surface area. so the interaction won't be as strong. And though it says the shape, I would also maybe add the size, which may add to the shape, because like if we're thinking about we're taking 2 oranges, we'll have 2 molecules shaped like oranges, right? Just just go along with it. But 2 oranges together, they have more surface area, both of them, to interact with each other versus an orange and a grape. Even though they're circular, they don't necessarily have to be flat. They're the same shape. One's just bigger. And so, yes, find the molecular shape because that affects it. Now we have to determine the polarity and the charges. Like I mentioned in the ions and cations, those create such a strong intermolecular force because they are so far, like on their extremes, right? One's really, really positive, one's really, really negative. And the more positive, I guess, like the stronger they are, like a super positive and super negative are going to have a very, very strong attraction versus kind of positive, kind of negative, not huge. And likewise, the polarity also plays into how they'll interact and what kind of intermolecular force we will see and how strong it'll be. And then it says, determine what intermolecular forces are present and compare their strengths. And likewise, like I said, the shape and the size and the charges will help you compare their strengths, but also just kind of like studying to the point where I think it would be helpful to know how to order them. Like, okay, it's strongest to weakest, London's, go down the list. I think that would be helpful. And also, not only will you should know which one's stronger, but you should know what each one looks like. Some polar, non-polar, cation, anion. Because if we don't even know how to see which ones are there, then I don't really know how we're gonna compare them, right? And then it says, think about how these affect things like boiling point, melting point, and solubility. And so I guess this is kind of like a broken down version of the whole picture of what intermolecular forces are, what each of one is, I guess, entails or needs to be stronger, or what makes it weaker, and how it affects melting and solubility. Because honestly, if we can figure out what force there are, we can probably always figure out, like, okay, this one has higher melting points, has higher boiling point, because a lot of our questions are phrased like that. And that's what we really have to worry about. Awesome. So that is all I had. But yes, I feel that, okay, I could jump, which is fine. But yeah, so the intermolecular forces are a really big part of the world around us. And a really big part, I don't know if it's going to be a huge part. Of course, it's going to be part of the final, right? But that's probably not a ginormous part. But, a big part of what we need to know in order to understand chemistry and just kind of understand how molecules interact and why things around us do what they do.